अगला वाला जो है वो भी इससे छोटा है क्या?
अगला
ये होगा ही
और
ऑब्वियस।
3 को भी साइड में ले लो, 3 को।
तेरे अरे कहाँ करते हैं? आवाज़ कहाँ से आ रही थी? सर्दी सरकार दाढ़ी बनवा के आ गया लौंडा। तुम्हें मोबाइल से आया होता
क्या?
आवाज़
अरे वो गाड़ी
सुगी बहन का लौड़ा छागी झांक तेरा सारा अरे भोसड़ी को कहाँ गए रे?
आलू 1100 संगीठी और ईठी लगा सकते हैं। वो हमारा चीज काम कम हो जाता है।
साफ बना हो
काय रखी है ना? काय नहीं कहे मकान में होती है।
कहाँ वो बाल हो काम हो रही है बाल हो काम
बाल धोए बाल बढ़ाओ।
बाल रहा काम करेगा बाल अपने आप बाल धोने का काम
तो बाल धोआ के कहे सनको आपको नहीं लगता?
तो शैम्पू केमिकल है इसलिए
भैया
सुन
Okay,
हाँ नाम बस
power is not yet back, but let me start.
कुछ इफेक्ट दिखाओ तो कहीं कर
My computer is going to shut down because the battery has probably got
कौन सा को
it's not there. So let me try to switch off from here and let me think if I can get in through my laptop. Okay, just hold on for a moment. I'll be out and I'll come back. Okay.
nhưng phải ở giờ
Hello. Hello.
bấm rồi tại cả
Bà chắc là
đó phải cho cái con này nó gì rồi mình tới ra khi trần चलो चल यार Gloria, por supuesto. Kalau saja Turki ya situ.
Okay, so let me share my slide with you. And okay, all right. Just hold on for a minute. All right, I think it is visible to you. Is the screen visible to all of you?
Yes, sir.
Yes, visible.
Okay, great. So we have been discussing about the design of a treatment plant. I mean sedimentation basin, where we have we tried to do a plain sedimentation basin, and so with a flow of 3 meter cube per second. And we first decided that we'll have at least 2 compartments, and then we ended up having three compartments, each having 92 meter by 18 meter space. And then what happened is that we proceeded with the design, and then we saw that everything was okay, but the Reynolds number was like failing because of the configuration of the system. Okay, so then we actually so we saw that the RH value is pretty low, so we wanted pretty high, so we wanted to make this RH radius of hydraulic mean radius value as small as possible. So we made each compartment into 3 horizontal. We put 2 horizontal baffles to convert each compartment into functionally 3 compartments, and then what was our design. So ultimately this was your so we had 3 basins where we had 92 meter by 18 meter each. So we actually had 54 by 92 meter space taken up by our basin. Okay, so there will be another some more space because we need to keep a space for for removal of treated waste, treated water and all. So then like 20% more, add 20% more here, so that you can create. So we are talking about a very large amount of area. So we decided that we will put a tube settler, and same we'll have 3 compartments, and then each will have modules of 50 millimeter square tubes. Vertical height of each of the tubes will be 0.6 meter, and horizontal angle with the horizontal would be 60 degree. So this is what we decided. Okay, and so each compartment, so we had 3 compartments, and each compartment would have 1 meter cube per second. Then, so you have 3600 meter cube per hour. And we calculated that the settling velocity of these particles are 2.2 meter per hour. Okay, and then what we did, we tried to find out what will be the area of each of this compartment if we provide tube settlers. So when we provided that, we could see that we put in this formula, so we found LP sine theta equals to our h or height. So this is 0.6 meter, and then we have, we plug in the numbers, and we found out, Q is 1 meter cube per second, and you have area here. So the velocity of settling will be 2.2. So we got an area of 242 square meter. So this is where we stopped in the last class. Let us, start, working out this problem and see whether we are actually meeting all the standards, Reynolds number, Froude number, and all. So each compartment will now have an area of 242 square meter. Now, when the tube modules are actually comes in square tubes, let me put another new slide here. Okay, so we need to first find out, we have got the area, but we need to also find out, how to configure this, the area. Okay, so actually we will take, so now let me, okay, so we have got an area of 242 square meter, right? So we have got an area of 242 square meter. So now let us consider that, sorry, oops. So we had 242 square meter of area. So let us consider that we have so let us consider that the assembly will be square in shape. I will try to. So if that be so, then length is 2 equals to width. So we have area equals to 242 square meter. So you can see length is 2, width equals to 242, which is almost 15.6 meter square. Sorry, meter. 15.6 meter. Now, so this will be the dimension of the tube bundle that we are talking about. So what will happen? You can see this, that we can have like let me say 15.6 by 15.6 area, where we will keep the tube bundles. Okay, so 15.6 by 15.6. Now this is not all. Then you have to have like about 20% extra space. 20% extra space for providing the inlet of water and all. So if you provide 20% extra space, so then this becomes, so let me take 25% extra space. So this will add this extra space here. So this is 25% extra space, and so 25% extra space. Okay, this is 15.6 meter. So what you get is like 21 meter as the total length of this top. So each of the compartments will have 21 meter by 15.6 meter space. Okay. So each of the compartments will have 15.6 by. So this is the amount of space that will be required by 21 meter. Now, how this arrangement would look like? These are tube modules that you will provide here. Tube modules. Okay, and this will look almost like, I'll come back to this, but here in this place we have tube modules right here. Okay, and module is like as you can imagine is, let me draw this. So each tube module will look like this. So this is our 50. So each tube module would look like this. So each of these modules will be right here. Okay, one after another in plan view. You can see this. This will be one after another put like this, and if you see that, the water will enter from the bottom and will come out from the top, and this will be collected, through a side channels. So you'll provide channels at the side, and they will be collected right here. So you have channels at the side, and they will be collected here. And so we need to see whether the norms are correct or not. First of all, find out the value of VH. We have not found out the value of VH theta, which is Q by A sine theta, right? Where theta is the angle created by here. Okay, each of those modules. So we have Q equals to 1 meter cube per second, and divided by 15.6 meters square, and you have sine 60, right? And so this actually gives me 4.74 into 10 to the minus 3 meter per second. So each of these will have a VH theta value of equals to 4.74 into 10 to the minus 3 meter per second. Now we want to find out the Reynolds number. We have seen that the Reynolds number has a role to play here. So Reynolds number, how to find out the Reynolds number? First of all, we have to find out the hydraulic mean radius here. So RH, so think about this particular tube, water. So this is a plan view, and this is like I'm showing one particular tube module here. So the water actually flowing through this tube module, right? So it is flowing through this tube module, and what is going to happen is that the weighted perimeter is the whole side, all the sides of the tube. So if I write weighted perimeter equals to so RH, hydraulic mean radius, equals to area by weighted perimeter. So area flow is 50 mm by 50 mm, right? So each of these tubes have 50 mm at the sides, and 50 mm square. Okay, and so you have 50 mm by 50 mm divided by, you have 4 sides are being weighted, so you have 4 into 50 mm, right? So you have I have calculated this, so this is 0.0125 meter. Okay, and so you can calculate RE equals to, you can write V is the velocity through this, and rho, okay, rho W into RH, okay, divided by mu, right? So you can plug in the numbers. So this is 4.74 times, okay, into rho W is 1000 kg per meter cube, okay, times you have 0.0125 meter, okay, and divided by 1.3 into 10 to the minus 3 kg meter per second. Okay, and when you do this, we have found out this value equals to 45.58, which is very much okay, because it should be below 20,000. Okay, so Reynolds number wise it is fine. So if you want to find out Froude's number, Froude's number is equals to V square RH into G. Okay, so if you plug in this number, you'll get to see this is 1.83 into 10 to the minus 4, which is greater than 10 to the minus 5, and we'll say this is okay. So we can see that so all the checks are fine. So we actually have now reduced the size of each of this chamber. Earlier, each of this chamber was 18 meter by 92 meter. So your whole thing was like 54 meter by 92 meter. So this was earlier for sedimentation tank. For the conventional sedimentation tank, this was the minimum dimensions that you need to take, but you have to have 25% extra, just saying, the way I have provided here. So all these things should be there, so you can imagine how much area should it take. Now we have drawn up, plan view. Let us also draw a view of the whole thing, I mean the sectional view, and that will be like okay. So we have so we have these modules. Let me first draw these modules here. So we have the whole modules here. So this is our module here. So here we have the tubes. I'm just trying to draw the elevation view of this. Okay, so we have seen the plan view in the earlier diagram, and so these are the tubes inclined at 60-degree angle. Okay, and the water will try to push through these small tubes, right? And now we have the height of 0.6 meter as per the problem statement. So this is the 0.6 meter height. Okay, now what are the other things that you need to provide? So normally we need to provide a sludge depth, or so it is very much required that we should have very quiescent condition inside the basin. So normally we like to provide depth of 2 meter below this. Okay, so that we can provide a quiescent condition, and so we can draw this. I mean the whole length will be like this. Okay. All right, and you have to provide like 1 meter above this, for the water to be collected, and so this is how the whole, so this is the, and then you'll have a collection trough like this here. So you have a collection trough here. So the water will come. You have to create a barrier somewhere here. So that the water comes from here, okay, and it actually gets into this, okay, tubes, and then it overflows and it collects into the overflow channel, okay, and this is how the dimensions should look like. So the total depth that we need to provide is, so you need to provide 1 meter above this. Okay, so this is 3.6 meter. All right, and now how to so this is, each tank would look like this. So you can see the plan view right here. This one is the plan view. The water enters from here. Okay, and then it goes up like this, and it gets collected at the side wares, and from where it is taken out to the clear water channel. So if you now look at the elevation view, the water enters from here, okay, and it there is a barrier here, so it cannot go in from here, so it goes out, goes from the bottom and goes up like this, and then it gets collected, and this is how it looks like. Okay, so we have, this is each chamber, and we have 3 chambers like this, 3 compartments. So you can think about how to arrange this thing. So you can arrange this side by side, or you can have a different arrangement. So you have 3 streams, each stream will have this much of area. So now you can understand, back to your whole problem, you can understand that yes, if we can design tube settlers in a very pragmatic way, that will give us a wonderful way of treating our wastewater, or treating our water with as minimum as possible, as minimum as possible interference or any disturbance, because you can see the Reynolds number value is so low, 45.58, which is very, very quiet zone, where through the water the particles can percolate particles can separate out or sediment or settle very nicely and efficiently. Okay, and normally what we provide is that the solids that will be coming out here, the solids will be taken out from here. You can provide a telescopic device like this. You can provide a telescopic device like this, or you can have, you can taper it further, and you can provide a upper bottom from where you can take it out using a valve. Okay, so anything can be possible. You can make the arrangements at your will. Okay, so this is what we needed to talk about sedimentation. You have done type 2 sedimentation probably in your BTech days. I am not going into the details of it, because the whole objective of this course is not to repeat, but to brush up our previous experience, previous knowledge, and go for the new knowledge. Okay, so I would like to stop here for the part of it. Now I will upload the slides onto the Teams page, and if you have any question or anything, please do ask me in the next class. I will after today's class, probably I will upload first set of tutorials for you, and it is your duty. As the 4th year students who have been my student before, they know that I give this as practice problems, and I am not fussy about your whether you solve it or and submit it to me. It's your duty to solve those things and get acquainted with the topic, and if you have any problem, any difficulty solving any of these homework problems, tutorials problems, I think you should contact me, okay, or you should ask me in the class. Okay, so now I will just tear down this sedimentation part, and I will start with a new chapter, which is filtration. Okay, so let me start with a new chapter for filtration. our new chapter is on filtration. Okay. So start with this slide. So when we talk about filtration in this particular class, we'll talk about, we'll have two different distinctions. We will say, granular filtration, because nowadays, as you know, there are, other types of filtration as well, which we call uh, filtration based on, membrane. So we are not going to talk about filtration, about the membrane right in this particular lecture, on this granular filtration thing. But again, after this filtration chapter, we'll move over to the membrane-based filtration. So I guess that you all have been exposed to this subject or the topic granular filtration before. And when we talk about granular filtration, with the name itself suggests that we use granules for doing the filtration. So how these granules work, and so depending on the size of the granules and size of the pores that we provide for filtration, we can actually have two types of filtration. One is rapid gravity filtration, rapid gravity filters, okay, and we have slow sand filters. We have slow sand filters, and there is another type of filtration which is called pressure filtration. There are other types of filtration. So these are pressure filtration. These three are definitely granular filtration, but there are other types of filtration as such. Those are known as cloth filtration, or filtration using so these are cloth filtration is one of those things, and this is cloth filtration is mostly used in wastewater, sludge removal and all, where we call they are also known as filter presses, or vacuum filters. So we are not going to discuss about all those filtration techniques. We will try to focus on what we know as rapid gravity filters. Okay, so all about rapid gravity filters, you have probably gone through these formulas in your BTech days about how to calculate the head loss through the filters and all. We'll have a look at it, but before that I want to show you, or we want to discuss about how a rapid gravity filter looks like in the real world. Okay, so I should have a probably if I would have a video with me would have been better, but let us try to follow what I'm saying, and if you follow word by word, then probably it will be better for you to understand what I want, how it works. Okay, so this is, if you see this figure here, so this is a rapid gravity filtration tank. Okay, and so this is just a exploded view, or like a cut through view of a rapid gravity filter. So you can see this is just nothing but a rectangular tank, so we have cut through this tank to show what is this inside. Okay, now so there are wash troughs. First of all, there will be wash troughs. Okay, so these are called wash water troughs or wash troughs, whatever you can name it, but this is what is this? This is a dual purpose trough which actually tries to uh, you know distribute the water on the filter bed, and also they are uh, they are very much useful to take out the water when you do the backwash. So when you backwash, you try to clean your filter, and all those foreign materials which were trapped in your filter, they want to come out, and you use these straps to take it out. Now first let me show you how this happens. So this is, let's say, from the outside, there will be a channel. You can see that if you think about, just try to imagine that we had the total, all the walls right here. Okay, so it's not just exploded view, all the walls right here. So you can see, if you try to extend these walls right here, what you will try to find out that there is a passage. This is, you can see this particular area. So this is nothing but like a passage of water. So the water is actually put in here in this passage, and only outlet through this passage. You can see this is this is just flushing with the wall of the filter. Okay, so if this is the passage of water, then water will actually come from outside. Let me show if I have a diagram. Okay, I will show you. Okay, all right, I don't have that diagram. Anyway, so if the water comes through this passage like this, and there is the the water actually now has to flow. There is no way other than flowing in this trough. So this is just like you can see this profile of this trough. This is like a parabolic or maybe semicircular trough here, and what happens is that water comes and the water overflows from this trough. Okay, so overflow, after the overflow from this trough, so this happens here also. So after the overflow from this trough, what is happening is that the water comes over, what we see here as filter bed. Okay, so we have this filter bed here, and when you see this filter bed, the water comes over this filter bed, and when on this filter bed, you can see that the water will pass through this, try to pass through this filter, this sand bed. Okay, so and below this sand bed there is a graded gravel. So the water will pass through this bed, and it will try to pass through this gravel. Okay, so what is this gravel for? Gravel is to support the sand layer on top of it, so that if these are the gravels, they will not allow this the sand layer on top of it to escape. Okay, so we have the layer of sand over the top of it. It will not allow the water to escape, sand to escape. But what is the role of this sand here? So if it is the sand layer, now the sand layer will trap all these small particles. So these are the sand layers. This is the sand particles here. So they will actually trap, the whatever we have here, our water with small particles, that will be, or the flocks. They will be flocks or the small particles. They will be trapped on this sand. Okay, and the sand is actually supported by the gravels, so that the gravel cannot, the sand cannot escape this thing. But water can very well percolate through all these things, and when it percolates through all of them, there we have lot of pipes, with perforation. Okay, so you can see these pipes, it is written perforated laterals. So all these pipes, the water will enter through these pipes, and then the lateral to a single, manifold or a bigger pipe. Okay, so the water will get into this pipe. So water will enter this pipe and actually travel through this pipe and come to the manifold. And when in manifold, they will also travel, and go out from here. So what you can understand that, the dirty water comes here, and this water passes through these beds, and they get collected, and the manifold takes it out. Okay, so the dirty, the all this dirt or the, particles, they get collected over the sand bed, and as the particles get collected over the sand bed, the the gaps between the sand, they get smaller and smaller, and we call it the sand bed is getting choked. And as it gets choked, what happens is that, it actually offers a lot of head loss for the water to pass through, because there is not enough pore to pass through. Okay, now then what will happen, the water level on the bed will start rise, and when it starts rising, we understand that the filter bed is getting clogged. Okay, so after it rises to a preset level, it is time for making a backwash. So backwash, for backwash, we also, use the same, laterals and everything. Now you can see that when we, when we do the backwash, we just try to reverse the flow. How we reverse the flow? Let me explain this with the blue colored, pen, so that that will be, you can understand it better. Okay, all right, so we will reverse the flow. How? See, now this, wash water or backwash water will, pass through here. Okay, so backwash water will pass through here, and as the water passes through, then, it will go in the reverse direction. So water now comes out through these small laterals, the pores of the laterals, and then the flow will be reversed. Okay, and the flow will be reversed, and so the particles which are there on top of this, they will get resuspended, right? And so when they will get resuspended, level rises, now it comes into the trough again, so it comes back into the trough, and then the water actually gushes out from here. Okay, and it gushes out, and you use the same channel here, to take the dirty water out. Okay, so this is called, and remember that during the backwash, everything is, all the flow, everything is now changed. Okay, so the direction is just reverse. Okay, so this is in a nutshell how this thing works, and this is another view of the, the channels. And, the channel that we are talking about, that was feeding the water, here, or taking the backwash water. This is called the upper gullet channel. Okay, so you can see this is upper gullet channel, and so you can see this, and so this is unfiltered water, and then there is a lower gullet which is filtered water. Now this is your filter. If you try to look at water troughs. Okay, so this is your sand bed. Okay, so this is your sand bed. Layer of here, which will be like sand maybe here, or here on the top layer there may be anthracite. So it is a dual media filter when we talking about anthracite and sand, and is and lying below the sand is a gravel layer. Okay, so the water comes out from here, it passes through anthracite bed or the sand bed here, and then it actually, so the water comes out from here, and then it passes, and it gets collected into the, the under drain, or after the gravel there is all this perforated laterals and everything. So, and they actually, produce this water. So, this is the two-story channel. You can see that upper story takes in the dirty water. So the dirty water comes in from here, okay, and the lower story actually, collects the treated water, and it can come out from here, okay. And when we are doing the backwash, the upper story is now, the lower story is now, lower channel is now the inlet, and upper channel is the outlet. Okay, so the whole thing reverses. Okay, so this is how the system looks like. The inside of the system looks like. And now next, let me show. This. The camera showing how it is running. So you can see this is. This is wash water channel. Okay, so these are wash water channel. So water on this wash water channel, and it just falls over the bed below. So in the bed below here, this part, this is all the filter beds. So these are filter beds. And you are seeing water standing over the filter bed, because you need a head of water to run this thing. So the water will only percolate if there is a head above this, right? So you get a head above this or a level above this. So here you cannot see the bed because the water is overlying on the bed, right? So this is wash water channel, and this is how the water goes in. And this is another view of all these things. So you can see now this is the submerged. You can see here all these submerged beds. Wash water channels are here. This is during the backwash, when the backwash is taking place. Okay, so these are now getting submerged. Okay. So, and this is another view of the whole thing. So this is, you can see, this is wash water troughs. Okay, so these are all wash water troughs here. So these are all wash water troughs right here. And sometimes, this is the pipe which actually feeds into the gullet channel. Okay, and so this is influent to the filters, and every filter box will have this type of influent. Okay, and at the below you can see that the clear water comes out and it's getting collected everywhere, and this is the effluent to clear water well. Okay, and also there is a, when you backwash water actually gets collected right into the drain here, and this is going out. So this is how this the whole work looks like, and this is you can see, and here this is another view of the thing. So here you can see that we have two layered bed, coal and sand, and then actually has a 3-layer coal, sand and garnet. So this is just an overview of the filtration tank and how it works. So in the next class, we'll discuss more about how the under drain actually is arranged, and also we will talk about what are the some theoretical aspects of the filter bed. Okay, so until then, so we'll meet again on Wednesday. Until then, just try to I'll upload this slide and try to have a recap of what we have talked about in this class. Okay. All right. Thank you for being with me in this class. I'll see you in the next class.